Now, something that we might be interested in jumping directly to is finding the constant of variation in a given situation. So for each of the following scenarios, we are going to find the constant of variation and then use that to set up the equation that describes each variation. In the first case, we say that y varies directly with x such that y equals 68 when x equals 4. Alright, so this is a case of direct variation. We saw that in the first problem. And this is set up very much like the definition, so what we can infer from this is that y is equal to k times x. And then we can use the additional information that's provided. We're told that when y is 68, x is 4, and vice versa. So, if we say 68 equals k times 4, that will allow us to solve for k, and then plug that back into the formula or the model structure that we know we should be using. So if we divide both sides of this by 4, we see that k equals 17, which means that our model should be y equals 17 times x. So our constant of variation, k, and our model, y equals 17 times x. The second exercise states that a is directly proportional to the cube of b, such that a equals 84 when b equals 2. So what's interesting about this one? We have a direct relationship, a direct variation, again, but this one involves the cube of b, so we're talking about a power situation. That means that we want to set this up. We know a varies directly with the cube of b. This has the slightly different wording from the ones that we've seen so far. That means that a is equal to some constant, the constant of variation, times the cube of b. Now we know this additional information. We're told that a equals 84 when b equals 2, so we can use that together with what we know. A equals 84 when b equals 2. So we're cubing 2 this time. That will again allow us to figure out what that constant of variation is. Now 2 cubed is 8, so we have 84 equals 8k. If we divide both sides of this by 8, we see that k is equal to 10.5. So there's our constant of variation. And our model, if we put this all together, we know a equals k, 10.5, times b cubed. So that would allow us to maybe figure out what a would have to be equal to when b is 3 instead of 2. Now, at the end of the last exercise, I promised we would look at inverse relationships involving powers. That is what's going on here in the third case. Here we are told that r varies inversely with the square of I. Now what that means, if you refer to that fourth definition in this section, that means that r is equal to, just like before, we'll have k over I, but now I would be squared. So that is how the power manifests when we talk about inverse relationships. Now in this exercise, or this part, we're told that for this particular variation, when r equals 0.3, I equals 2.2. There's a decimal place missing right there. 2.2. Okay, so we can set that all up. We know 0.3 is equal to k, which we don't know yet, divided by I, which is 2.2 squared. Okay, that allows us then to calculate the value of k. We multiply both sides, we see that k is equal to 0.3 times 2.2 quantity squared, and that is exactly equal to 1.452. So our constant of variation is a little less pretty in this case, but we can use that together with what we know about the overall structure of our model, again, to set up the equation that relates r to I in this case. We have r equal to k, 1.452, divided by I squared. And that will always hold, so we could plug in different values for r or for I and see what other relationships arise from this variation. The next type of variation that we're going to look at is a little bit unusual and possibly the first time you're seeing something quite like this.